sorry about the interruption in the video. So we're still doing example 2, where we last stopped at the idea that in number 2, if we know that the distance from A to B is 5 miles, and we measured it to be 6.6 centimeters, then 6.6 centimeters is to 5 miles, as 1 centimeter is to, I scaled it down by 6.6, 1.32 miles. Okay, and that tells me that this height, which was measured to be 1 centimeter, is now 1.32 miles. And that this distance from A to B on the bottom is 5 miles. So, let's see. If we were going to measure from here to here, then all of a sudden we actually do need to use the Pythagorean theorem. And so this distance, we're going to have to go, 5 miles. And this is 1.32 miles. And we're going to have to go 5 squared plus 1.32 squared equals c squared. Okay, so 5 squared, 25. 1.32 squared is 1.7424. And that, if we add that, we get 26.7424. But we haven't taken the square root. This would be c squared. So we have to square root this. And if we do that, so c is approximately, and I definitely have to round now, I'm going to go 5.2 because we don't want to say we know more precision. This distance, or 5.17, is what my calculator wants me to say, is about, okay, so this distance, about 5.2 miles. Okay, so far we've ranked these two correctly. Now let's talk about the logic of our third one. Okay. I can probably estimate this using 2 triangles. I remember in my classroom, a lot of people were like trying to use a string or something, and I was like, what? Where did you even get a string? Let's see. This is a decent estimate for that length. It would be a little bit more. Okay, so I'm actually going to go like this. Okay, and from here to here, we can connect these two and say that's a pretty good estimate from here to here. Okay, so now, oh, is this half of that? That looks like almost like half of that. About 3.3. So halfway between, we have these two right triangles that we can use to kind of estimate how far along this path they went. Well, if this distance right here is 3.3 centimeters, so 6.6 centimeters is 2, so let's scale this down by 2, or half of this. Half of that is 3.3, and half of 5 is 2.5. All right, that's good. And then how tall is this? 1 centimeter. Well, that's nice. We already scaled that down. It's 1.32. Okay, so now we have 2 distances that we are finding. So let's go with this first one. And we know that the base of this is 3.3 centimeters, so that's 2.5. 2.5 squared is, I'm going to label it 6. Oh, wait a minute. So I'll go 2.5 miles here, 2.5 miles here, and this is what, 1.32 miles. So that I can use a squared plus b squared equals c squared. And I'm going to do it twice. Oh, and then there's two of them. Ooh la la. Okay, so 2.5 squared is 6.25. 1.32 squared was 1.7424. If I add those, I get 7.9924. And then if I take the square root of that, I get about 2.83. I'm not sure if I'm going to need that level of precision. I'll go 2.8 about. Okay, so that means this distance is about 2.8. Okay, so now let's label some stuff. I see 2.8 miles. I see 2.8 miles because they're the same triangles actually, just facing different directions, and that plus that makes 5.6. Oh my goodness, we actually really did get it. So shortest 5 miles, middle about 5.2 miles, and then this one 5.6 miles. Okay, so we really were able to do this. Sorry that I wanted to jump to an analysis before maybe trusting my gut. So suppose that distance was 5. Estimate the distance traveled along each path. We went up there and we actually did that. The grade of inclination on the third path is 10%. Find the distance. Okay, so we actually found the distance on this third path, but I'm not sure if it actually is 10%, but I want you to see what this is talking about. So this 10% business, a lot of road signs actually use this, the gradation, I want to say is what they call it, a gradation amount. So what this means is that if you know the base, you take this percentage of the base, so 10% of 5 miles. What is that? 0.10 of 5 equals 0.5. This is actually, you know, I really should have, this percentage I believe is actually a 5% in terms of this actual picture. But nonetheless, I still want to show you what this means. If it, the grade of inclination on the third path is 10%, find the distance from A to C. 10% of the base is 5 miles. I'm sorry, 10% of the 5 miles is a half of a mile. And then what this means is that that length from A to C is the base plus that 10%. Okay, which we know it's actually more like 5.2 based on actual measurements and scaling. So what I want to say about this is actually I think that they got the grade wrong. I really do think, yeah, I really do think that's a flaw. And I am saying it out loud, a flaw in the text. So I actually feel like this is more like 5%. Okay, and how that would change it is it would go 5% of 5 miles. Okay, 0.05 of 5, which equals 0.25, and 5 miles plus 0.25 miles is equal to 5.25. Okay, and notice how I keep my units. We want to make sure we're not doing centimeters on accident, and we are sticking to the one measurement at a time. Okay, so it is incredibly important to keep your units. Nonetheless, I believe it is actually closer to a 5% grade of inclination. Okay, let's keep talking about distances, but now we're going to put them on a grid. Okay, so instead of just having triangles floating in space, let's name that space and grid that space and say, where are they in space? So plot the point 0, 0. Got it. And the point negative 3, 4. So 1, 2, 3, 1, 2, 3, 4. Done. On the grid, find the distance between these 2 points. Okay, I'm going to zoom in. So first, okay, here's the line that we are trying to find the distance between, or the points that we are finding the distance between. So I connected them with a line, and I am going to form a right triangle out of these. So here's one distance, and that is a distance of 1, 2, 3, 4. And now I can't label it with centimeters because clearly they're smaller than centimeters, but I can call it 4 units. Whatever these little squares are, those are the units I'm going with. And then here is another side where I know its length. Was that 3 centimeters? Or I'm sorry, 3 units, not centimeters. And then we don't know this last length, but we can find it because it is a right triangle. Boop, boop. Okay, so just like we were doing on the last problem, we can write, okay, let's see, shorter side, hypotenuse. 4 squared plus 3 squared. Okay, well that is equal to c squared, whatever that is, yeah? And now all of a sudden, since we're on a grid, and I didn't necessarily, say that it was C, and the C was kind of for triangles floating in space or whatever, just very vague. I'm going to call this D because it says find the distance between these points. So I'm actually going to call this D for distance, and that means I just changed the name of that variable there. We've done this a lot, change the names of variables to go with what we want them to be understood as. So I'm going to call that longest side D for the distance I want. So 4 squared is 16. 3 squared is 9. And that is equal to D squared. Let's see, 16 plus 9 is 25. So the distance, well, what squared is 25? 5. 5 squared is 25. So this distance between these 2 points, 5. Okay, so we just made a grid, which means that we weren't using centimeters anymore, but we were using units. We plotted these 2 points, and we were able to create a right triangle that let us find the distance. Let's do it again. Okay. Plot the points 5, 1, 1, 2, 3, 4, 5, 1. Check. 8, 5. Oh no. 8 is out here. So 1, 2, 3, 4, 5, 6, 7, and that's 8, but I need it to go up 5 now. Okay, I have a ruler. I'm going to use it on my behalf. You can use a sheet of paper if you want to. 1, 2, 3, 4, 5, and, okay, 8. So, right about there. All right. Okay, so here's our point 8, 5. And now our job is to find the distance between these two. Okay. Let's call it D for distance again. And okay, its base. Okay. Okay, so I'm gonna go along this grid. Its base is 1, 2, 3 long again, 3 units. And its height, okay, so here is what? 1, 2, 3, 4 units tall. Okay, and look at that. We have formed a right triangle whose legs are 3 and 4. Very similar to this one. As a matter of fact, identical to that one, just flipped and moved. Yeah? So this triangle is actually the same as that triangle, and we would use the same exact steps. So let's do that quick. Okay, Pythagorean. And then 16 plus 9, 3 squared is 9, is equal to d squared, and that is 25. D equals 5. Distance of 5. So even though they were at 2 different locations, we went through the same process and they were actually the same triangle, just flipped and shifted. Let's do it again. Plot the points. -1, -6. Oh man, it goes to 10. It goes to -10. So I feel like moving my axis, because this one went to 8 and it should have been one. I see now that it's a little too long on that base, but should have just been 1 outside, but this would be 2 outside. That's going to be challenging for me. So if I just shift this axis maybe up, then I think we'll be okay. So I'm going to take our horizontal axis and shift it up 3. Okay. I used a regular. I didn't change these ones at all. Okay, but I definitely feel like I should here. Okay, and let's plot. -1, -6. -1 and 1, 2, 3, 4, 5, 6. Got it? -4, -10. 1, 2, 3, 4 to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 below. Got it. Okay, connect them. Label it with a D. So far, so good. Find the distance between these 2 points. I'm going to use the same exact process. Here we go again. I see that I can create a right triangle. Here's the base. That is 1, 2, 3 units long. I see that I can create a vertical here. Draw that in, and that is 1, 2, 3, 4 units tall. And it looks to me like I have the same exact triangle all over again, where the shorter 2 sides, which are adjacent to the right triangle, where the hypotenuse, the longest side, is always this diagonal one, is, let's see, 4 squared plus 3 squared equals d squared again. So 16 plus 9 is d squared again. That's 25. D equals 5 again. Okay, so wait a minute. We are saying that these 3 triangles, they are at different locations in space and rotated differently, like flipped, whatever, right? But their measurements are the same. So these three triangles are the same triangle, just in different spots. And if I know the measurements of one, I know the measurements of all. So we're not really fixed on these coordinate locations. We're really fixed on this 3 and this 4. That was what was consistent throughout all of those. Huh. Okay, so I'm wondering how we look at these coordinate pairs and think of where does the 3 come from and where does the 4 come from? Like here, this 3 came from the distance between 0 and -3, and this 4 came from the distance between 0 and 4. Does that work here? The distance between 5 and 8 is 3 along the x's. The distance between 1 and 5 is 4 along the y's. Is that true here? The distance between -1 and -4 is 3 along with the x's. And along the y's, the distance between -6 and -10 is 4. Ooh. So that's good news. Let's see if that pattern holds for this problem. We have to go down to -8. I am going to move my axis up again. What did I move it up 3? Seemed to be okay. Okay, so where are we at? -1, -6. -1, so 1 to the left, and 1, 2, 3, 4, 5, 6 down. -4, -8. 1, 2, 3, 4 to the left. 1, 2, 3, 4, 5, 6, 7, 8 down. I'm not gonna lie. I feel like that is a shorter distance than this was. Let's see if that's the case. I'm going to build a right triangle all over again. Here we go. The height of this is 2 units. The base of this is 3 units. So now all of a sudden, the 2 shorter sides are 2 squared plus 3 squared equals d squared. Right on. 2 squared is 4. 3 squared is 9. And that is equal to d squared. 4 plus 9 makes 13. Uh-oh. Square root? So I don't know what squared gives 13. I knew what squared gave 25, but this, ay. So I'm gonna leave it as the square root of 13 and maybe put in its approximation from the calculator. Okay, so I'm gonna do the square root of 13. I get about 3.61. Roughly speaking. So this distance is approximately 3.61, or is precisely equal to the square root of 13. Notice it is a little bit shorter. Okay, and the difference between these two is this 2. Ooh, look. In the y's, -6 and -8 are 2 apart, instead of -6 and -10 being 4 apart. Okay, I'm beginning to see where all of these different measurements are coming from. So let's create a distance formula. So it seems to me, in order to find these distances, so I'm going to use this example to kind of pave my way here. Well, we had to take the square root because it was a square. So in the end, we definitely need a square root. So d equals square root. And I kept noticing that first this 2 came from the, oh, my 2 is actually the change in the y values. That's where this 2 came from. Okay, so change in the y values. change in y squared plus the change in x. So these, how far apart are -1 and -4? Those are the x values, and that gave this 3 here. So change in x squared. So we would find the change, square it, find the change, square it, then add, and then take the square root. Find the change, square it, find the change. Okay, so find the change first, then square those two, then add, then take the square root. So the order of operations, find the change, then square, then add, then square root. Okay, got it. And that is, so how do we find the change again? Well, we had created a formula for this, and we still do the same. In order to find the change, you just subtract the two values. So to find the change in the y's, we would do y2 minus y1, or y1 minus y2, it doesn't matter, by the way. Square it. And the change in the x's, that's its difference as well. Okay, so here is our distance formula, and I need you to know at the end of the day, this all comes from the Pythagorean theorem and the steps we took to use the Pythagorean theorem. All right, remarkable thing number 1. The distance formula is based on the Pythagorean theorem with the addition of a coordinate system. So the distance formula comes from applying a coordinate system or a location system onto right triangles. And using Pythagorean theorem. Yes? And that means, so my next remarkable thing is that means if you get stuck, worst case scenario, you can make yourself a right triangle. So if you forget the formula, draw yourself a right triangle and use Pythagorean. Yeah? I mean, if you forget this, because it looks pretty fancy and like high tech, but it's really not. It's really just us using the Pythagorean theorem. So if you forget that formula, just go ahead and draw yourself a right triangle and apply the theorem to it. Okay? In the next video, we'll go ahead and finish up this section looking at this cool example. I was so proud of the authors of your textbook for using this example because I just never really found contour maps all that exciting and fun until I saw other mathematicians using them as examples, and I was like, yeah, that is really applicable. So anyway, in the last video, we will do that example because it is pretty cool.